Hello everyone, welcome to Probability and Statistics for Data Science. Up to now in the course we have learned how to build models that had multiple discrete variables and also models that had multiple continuous variables. But in probabilistic modeling we often need to consider discrete and continuous quantities at the same time. In this video we're going to learn how to jointly model discrete and continuous quantities within the same probabilistic model. The way we do this is by representing them as discrete and continuous random variables within the same probability space. We're going to learn how to characterize the joint distribution of those variables. Our goal is to be able to manipulate discrete and continuous quantities within the same probabilistic model. Remember that we have two kinds of variables. Deterministic variables that have fixed values are just represented like this, without anything on top. But when we consider random variables, we always write them with a tilde or a squiggly line on top. This indicates that this is a random variable that we need to describe in terms of a probability. We cannot just say a is equal to 3. We say the probability that a is equal to 3 is, for example, 0.5. But what is a random variable? We have talked about this quite a bit in the course, but it's really important to make the distinction between how we define random variables mathematically and how we manipulate them in practice. If you ask a data scientist what is a random variable, what they will tell you is that it's a variable that represents an uncertain quantity within a probabilistic model that they manipulate using probabilities that they estimate from data. If you ask a mathematician what is a random variable, they're going to give you a very different answer. They will tell you that it's a function from a sample space to either a discrete set or the real line. However, we have seen in previous videos that this mathematical framework is built so that these probabilities that the data scientist is interested in are well defined. So there is this connection between the two viewpoints. In this video, we're going to see how this framework allows you to manipulate discrete and continuous quantities together. In order to do that, let's remind ourselves how we model discrete and continuous random variables separately, and then we will see what happens when a discrete and a continuous random variable are defined within the same probability space. So here we have a sample space in a probability space associated to a random variable a that can have three possible values, a1, a2, and a3. What we saw is that we can partition the sample space into the outcomes that map to a1, the outcomes that map to a2, and the outcomes that map to a3. And in order for the discrete random variable to be well defined, the probability measure of the probability space must assign a probability to each of those events. So then we can talk about the probability that the random variable is equal to a1, a2, or a3. And what we typically do is we encode those probabilities in the probability mass function of the discrete random variable, and that's what we use to manipulate the random variable. We forget about the underlying probability space. The probability mass function is the user interface of the discrete random variable, in the sense that that's what we really use to compute probabilities associated to the random variable. It tells us the probability that the random variable equals each of its possible values. This is what we actually estimate from data. What about continuous random variables? In the case of continuous random variables, we cannot describe them in terms of the probability that they are equal to individual points, because these are continuous quantities and that probability is going to be 0. Instead, we characterize continuous random variables in terms of the probability that they belong to different intervals. So here we have these two example intervals within the real line. If we have a random variable defined on a certain sample space of a probability space, then we can take a look at the events that map to the different intervals through that random variable. So here A maps all of these guys to this interval and all of these guys to this other interval I2. In order for a continuous random variable to be a valid random variable, all of those events of this form that map to an interval on the real line must have a well-defined probability. The probability measure of the probability space must assign them a probability. In order to manipulate and describe the random variable, we can just use those probabilities and forget about the underlying probability space. How do we keep track of all those probabilities? We use the user interface of the continuous random variable, for which we can either use the cumulative distribution function that tells us the probability that the random variable is more or equal to any value on the real line, or alternatively, we can use the derivative of the CDF, which is the probability density function, which tells us locally how much probability density does the random variable have at any point on the real line. These are the quantities that we actually use to manipulate the continuous random variable. These are the quantities that we learn from data. Okay, so we have finally reached the point where we can address our main topic of interest here, which is how do we jointly model discrete and continuous random variables? Discrete and continuous quantities. The way we do that is we define them as random variables within the same probability space. So let's take a look. What we want to do is define these random variables so that we can talk about the probability that the discrete random variable is equal to a certain value, and at the same time, the continuous random variable belongs to a certain interval. So for example, here we might have a random variable C and a random variable D, and the random variable D has two possible values, D1 and D2. The continuous random variable can be anywhere on the real line. So we want to be able to talk about events of the form the random variable D is equal to D1, and at the same time, the random variable C is within this interval C. In 2D space, you can kind of think of this as being at this point where, this, like D basically is equal to this or this, the random variable D, and then C is anywhere on this line. So you are asking, what is the probability that I'm on this line here, where D is equal to D1 and the random variable C is in that interval. Realize that the horizontal axis is not discretized, it's continuous, but the vertical axis is discretized. We can only be, in these two different points because the vertical axis corresponds to a discrete random variable that can only have two values. Okay, so then let's ask ourselves first about the probability that the discrete random variable is equal to that value that we're interested in. Okay, it's equal to D1. As we had explained, if we go to the sample space and the underlying sample space is going to be partitioned between the values that map to D1 and the values that map to D2 through that discrete random variable D. Okay, so that probability is well defined. The probability that the random variable D is equal to D1 is well defined as long as D is a valid discrete random variable. What about the probability that the random variable C is within that interval? Well, that's also going to be well defined because in the underlying probability space, this event of all the outcomes that map to that interval through C must have a probability assigned to it by the probability measure, because otherwise the continuous random variable would not be a valid random variable. The key thing to realize here is that this is the same sample space. So now, what is this event that we're interested in, where this 2D vector composed of the continuous and the discrete random variable as entries belongs to this segment here, where this entry is equal to D1 and this entry is within that interval. What outcomes in this sample space are going to map to that line? Well, those outcomes have to be in D1 because the second entry maps to D1 but through D. The second entry, is equal to D of omega, that is equal to D1, the second entry of this 2D vector. And at the same time, they have to be within that event because the first entry maps into the interval. So we're basically interested in the intersection of those two events. But if we remember, by the properties of probability spaces, if we assign a probability to an event and we assign a probability to another event, we also need to assign a probability to their intersection. So this essentially states that if we have well-defined discrete and continuous random variables within the same probability space, automatically these events that we might be interested in, where the discrete random variable is equal to a value and at the same time the continuous random variable is in an interval, those are well-defined automatically. So now we can see some of the power of this mathematical framework of defining random variables as functions from a probability space to the real line or to discrete set. It allows us to encode the to define the joint distribution of many random variables that can be very different in a pretty elegant way. Okay. All right, so what about the user interface? So we saw that for discrete random variables, the user interface, for multiple discrete random variables, the user interface is the joint PMF that tells us the probability that they equal certain values at the same time. Can we do that here? We cannot, right? Because one of the random variables that we're interested in, which is continuous, has zero probability of being equal to each value. What about the joint probability density function, which is how we model multiple continuous random variables? This is the user interface for multiple continuous random variables. Can we use it to characterize a discrete and a continuous random variable at the same time? No, because the discrete random variable does not have a density. This is not completely true, because you could use Dirac deltas to represent the density of a discrete random variable, but things get very complicated. You have to introduce distributions. You could potentially do this here, but it gets a little bit mathematically hairy for no reason. Instead, but this is commonly done. For example, in signal processing, some people do this. Can we use the joint CDF? The joint CDF would tell us the probability that the discrete random variable is smaller or equal to a certain value, and at the same time, the continuous random variable is smaller or equal to a certain value. Yes, this is going to be well defined. However, we already saw in the video on multiple continuous random variables that it's just a pain to use joint CDFs. Like, it gets very complicated. It's really not pleasant, but you could in principle do it. So what are you going to do instead? We want a user interface that is easy to use, that we can estimate easily from data. Instead, what we're going to do is we're going to use marginals and conditional distributions. We're going to see how in some examples. Okay? So let's consider a discrete random variable D and a continuous random variable C. So for example, we might ask about the probability that D is equal to a certain value and C is smaller or equal to a certain value. What is this equal to? By the chain rule, it's just the probability that D is equal to some value, to that value, and then times the conditional probability that the continuous random variable is smaller or equal to the value of interest, conditioned on the discrete random variable being equal to D in this case. So this immediately is the PMF of the discrete random variable. No problem there. That's what we usually use to manipulate the discrete random variable. Here we have an interesting object arise, which is the conditional CDF of the continuous random variable given the discrete random variable, which is well defined, right? It's just the probability that the conditional random variable is smaller or equal to a value, given that the discrete random variable has a certain other value. Now we can actually define the density of probability of C, because we like using densities. Densities are easy to use, they're intuitive to interpret. We like doing that. Conditioned on the discrete random variable being equal to a certain value, in the same way that we did when we were just defining the marginal probability density function of a random variable. It's going to be the probability that the random variable, the continuous random variable, is within a certain interval of width epsilon divided by epsilon, but now we're conditioning on the discrete random variable being equal to a certain value. And what we see is that, by the same argument that we used in the case of the marginal PDF, we can easily show that this is just equal to the derivative. Why? Because the probability that the conditional probability that you're in that interval is just the conditional CDF at C minus the conditional CDF at C minus epsilon. When we divide by epsilon, what do we obtain? well, the derivative, when we take the limit of epsilon going to 0, the derivative of the conditional CDF. All right, so we're going to see that using these two objects, the probability, the PMF of the discrete random variable, and either the conditional CDF or the conditional PDF of the continuous random variable is a very natural way of manipulating discrete and continuous random variables at the same time. Let's take a look at an example. We're going to take a look at the temperature and precipitation at Mauna Loa, which is a volcano in Hawaii. These are the original data are hourly temperatures and hourly precipitation values. And precipitation is just going to be 0 or 1. So here we see that most of the time there's no precipitation. Sometimes there is some precipitation. This is the PMF of the discrete random variable. Now, more interestingly, let's take a look at the continuous PDF of the conditional PDF of the continuous random variable given the discrete random variable. How do we estimate this? Well, it's pretty easy. We just check when the precipitation is equal to 1, and then we use kernel density estimation to approximate, here we have it, the conditional PDF of temperature given that there is precipitation. How do we compute the other conditional PDF? We just check the points for which there is no precipitation. We apply kernel density estimation to those points. Boom, we get the conditional PDF given no precipitation. Here we see something quite interesting, nothing to do with discrete and continuous random variables, but it turns out that it probably snows on that volcano, even though it's in Hawaii, or at least that's how I interpret the fact that near 0 Celsius, we have this peak. Of course, this doesn't happen very often, but still, it's interesting. So what I'm interpreting is that this must be snow and this must be rain. This is how I interpret this weird bimodal conditional distribution. In contrast, when there's no precipitation, the conditional PDF is unimodal. It looks much more normal. So yeah, we see some interesting stuff arise when we consider the conditional distribution between temperature and precipitation. Okay, so now let's talk a little bit about how we manipulate these objects. Imagine that you know the marginal PMF of the discrete random variable, and you know the conditionals given the values of the discrete random variable, just like we did for the precipitation and temperature at Mauna Loa. How do you derive the marginal distribution of the continuous random variable? Without, you don't want to worry about the discrete random variable, you just want to isolate the behavior of the continuous random variable. So what do we do? As usual, when we want to characterize a continuous random variable, we compute its CDF, because that's what has a very intuitive meaning, which is just the probability of this event that the continuous random variable is more equal to a certain value. We always do this, right? When we're trying to derive something about a continuous random variable. Now, how can we express this event in terms of the discrete random variable? Because this is the information we have, right? We know the PMF of the discrete random variable. We know the conditional PDFs. Well, what we're going to do is we're going to use the law of total probability, and we're going to say that this event is equal to this event conditioned on the possible values of D. So here I should have written D equals D. Okay, sorry about that. And is summed over all the possible values of the discrete random variable. So here the range of the discrete random variable is this big D. So what is this by definition? It's just the CDF, or the conditional CDF of the continuous random variable given the discrete random variable at that value of interest, okay, the value that we're interested in originally. So now, if we want the PDF, we just need to differentiate, realize that these are just constants. When we differentiate, we get the probability density, the conditional probability density function of the continuous random variable given the discrete random variable. This is really nice because it kind of mimics the formulas that we had to compute the marginal PMF of a discrete random variable given its joint PMF. Remember, we summed over the other variables. And here, when we want the marginal PDF of the continuous random variable, what do? We sum over the discrete random variable. Of course, like we have to multiply the PMF by the conditional PDF. So here, in the case of discrete random variables, we had the joint PMF. Now we do not have the joint PMF. We have the marginal times the conditional, but the chain rule, in the case of discrete random variables, we would also have had the marginal PMF of one of the variables and the conditional PMF of the others. So this is analogous to the formula that we had for discrete random variables, except that now for the continuous random variables, we plug in densities instead. And this is mathematically justified because of this argument. Okay, so let's take a look at what we actually do. So we have these two conditional PDFs. What are we going to do? We're going to multiply the one given precipitation by this probability and sum it to the conditional PDF given no precipitation multiplied by this probability. So obviously the one with no precipitation is going to dominate. And well, first let's actually write this down. What is the density? We have to multiply each of the values of the marginal times the corresponding conditional density. And when we do that, boom, we have something that is dominated by the conditional density given no precipitation. All right, now let's consider another data set where we have this is a data set from the US Army where there's 4,000 men and 2,000 women. Okay, and we want to model their height. We want to design a parametric model for height. Let's see what we do. So if you remember, we already used this data set when we were talking about parametric models for continuous data. We modeled the height of the men as a Gaussian. So let's just model the height of everyone as a Gaussian. And what we see is that the model is not great. This is the maximum likelihood estimate. This is the best possible fit of a Gaussian to this data. When we compare the Gaussian model, which is this solid line, to the histogram of the data, the fit is not great. It seems that we're violating the assumptions in the Gaussian model. So what can we do? Well, we realize that for just the men, we get a fantastic fit. So how about we model height as a continuous random variable that depends on the sex of the person, and those conditional PDFs of the continuous random variable given the sex are Gaussian, because we know at least that the one for men is Gaussian. We're going to see in a moment that the one for women is also well approximated as Gaussian. Okay, so this is basically a Gaussian mixture model. That's all a Gaussian mixture model is. You realize there's a discrete random variable that is important in characterizing the distribution of the data, and conditioned on that, the data is well described as Gaussian. If that is the case, then you can apply a Gaussian mixture model. So now let's ask ourselves about how we are going to characterize the distribution of this Gaussian mixture model, where we have the joint distribution of sex, which is discrete, and height, that is continuous. How do we estimate the distribution of S? Well, with the empirical PMF, right? We take, for example, the number of women and we divide by the total number of data, and that gives us the probability of women. The probability of men is just 1 minus that. So this, we just use the empirical PMF to estimate the PMF of the discrete random variable. Now, how do we estimate the conditional distribution of the continuous random variable given women? Well, it's very easy, right? We take the data, we separate it, we take only the data corresponding to women, and we apply maximum likelihood estimation. The mean is going to be the average, and the standard deviation, we saw the formula. It's essentially, it's very close to the sample standard deviation. So when we look at the fit that we obtain for women, it's actually pretty good. Here the mean is 163 centimeters with a standard deviation of 6.4 centimeters. What about for men? We do the same thing. We separate the men in the data, and for them separately, we compute the mean and the standard deviation using maximum likelihood estimation. The mean is higher, it's 176 centimeters. The standard deviation is a little bit higher, 7 centimeters. And again, the fit is very good. So now, what if we want to compute the marginal distribution of height? Okay, we want to model, like have the a PDF for height. Well, we apply our formula where the PDF of h can be obtained by weighting the conditionals by the corresponding value of the marginal PMF. In this case, there's two possible values, so we just sum them. Each of them is Gaussian. Here, I'm representing the probability of women by pi of women, probability of men by pi of men. Realize that these are just the values of the marginal PMF, so they add up to 1. And the rest is, are the Gaussians, that are the conditional PDFs with the appropriate parameters, right? So the standard deviation for women, the mean for women, mean for men, standard deviation for men. So when we put that together, we get a very good model of the height of the whole population, indicating that the assumptions in the Gaussian mixture model are quite reasonable. The sexes can be modeled separately as Gaussian, but when we put them together, they cannot really be modeled as Gaussian. Okay, so what have we learned? We have learned the definition, the mathematical framework that allows us to jointly model discrete and continuous variables as random variables within the same probabilistic model. We have learned about the user interface of these random variables, which can be the marginal PMF of the discrete random variable and the conditional PDF of the continuous random variable given the discrete random variable. And we have used these concepts to build Gaussian mixture models that allow us to define parametric models that are more flexible where we're conditioning on a discrete random variable. And that's all I got. Thank you very much.